Hello, this is Matt Dean with A Plus College Ready, and today we're going to work some stoichiometry problems. We'll begin with some composition stoichiometry problems. This first problem is determining how many grams are in 3.20 moles of calcium chloride. So the first thing that we're going to do is write out our given. So that's 3.20 moles of calcium chloride. We're going to draw a little dimensional analysis chart. 1 mole, we're going to put down here on the bottom. And on top of our chart, we're going to put the molar mass of calcium chloride. So you need to add up the mass of 1 mole of calcium and 2 moles of chlorine. When you do that, you get a molar mass of 110.98 grams. Now notice we put out the part of our conversion factor that we put on the bottom was the mole portion, so that this part could cancel out with this part. Now all we have to do is multiply, and when we do, 3.20 times 110.98, we get a final answer here of 355 grams, and that is of calcium chloride. All right, so now we're going to move on to problem 2. And I'm going to make some space and work it in the blank space above problem 2. So now we want to know how many molecules of water are in 98 grams of water. So we're looking for molecules. So first of all, we need to take our 98 grams of water. And pretty much our first step in most of these problems is going to be to convert to moles. So we need to determine the molar mass of water. So we'll add up the mass of 2 moles of hydrogen and 1 mole of oxygen. When we do that, we get 18.01 grams of water. And that's how much water is in 1 mole. Notice we put the grams on the bottom so that grams will cancel out. But we're not trying to find moles in this case. We're trying to find how many molecules of water. What we need to know here is that 1 mole of any substance is equal to Avogadro's number, 6.02 times 10 to the 23rd particles of that substance. And in this case, the kind of particle we're looking for are molecules of water. The moles cancel out, so we multiply 98 times 6.02 times 10 to the 23rd. We divide that all by 18.01, and when we do that, we end up with a final answer here of 3.28 times 10 to the 24th, and that is molecules of water. All right, now we're ready to look at problem 3. Here we want to know how many hydrogen atoms are contained in 98 grams of water. Well, in the previous problem, we converted the 98 grams of water to molecules of water. And we got 3.28 times 10 to the 24th molecules of water. What we have to realize here is that in each molecule of H2O, there are 2 hydrogen atoms. So that's our conversion factor. We're going to say for every 1 molecule of water, there are 2 hydrogen atoms. We put the molecules on bottom so they'll cancel out with molecules over here. We multiply, and when we do, we end up with a final answer here of 1.28 So let's go back. When we multiply 3.28 times 10 to the 24th times 2, we end up with 6.56 times 10 to the 24th. And that is atoms of hydrogen. So that's our answer to problem number 3. For problem number 4, we want to know how many moles of oxygen gas are contained in 9.00 times 10 to the 25th molecules of oxygen gas. So again, this is another composition stoichiometry problem. We're going to start with our given. So 9 times 10 to the 25th molecules of oxygen. And what we have to realize here is that in each mole, there are Avogadro's number, 6.02 times 10 to the 23rd molecules of a substance. So we're going to put 6.02 times 10 to the 23rd molecules down here at the bottom of our conversion factor. And we're going to put what that's equal to up top, which is 1 mole. We put the molecules on the bottom, so they would cancel out. So now it's a matter of going 9 times 10 to the 25th times 1 and dividing it by Avogadro's number, 6.02 times 10 to the 23rd. And when we do that, we end up with 150. To get our sig figs right, we're going to put a decimal point there at the end, and that is moles of oxygen gas. So now we're going to move on to problem number 5. What is the mass of 9 times 10 to the 25th molecules of oxygen gas? Well, in the last problem, we converted from molecules to moles. So let's start with those moles this time. So we had 150 moles of oxygen gas. And now when we're converting to mass, we're trying to get to grams. So what we have to realize is that for every mole, we need to put in the molar mass of oxygen gas. So take the molar mass of oxygen twice. Well, that turns out to be 32.0 grams. So now it's a matter of multiplying 150 times 32. And we end up with 4.78. And that is times 10 to the third. And that's grams of oxygen gas, O2. All right, so now we're ready to move on to problem number 6. Problem 6, we're at our first reaction stoichiometry problem. In the neutralization reaction between hydrochloric acid and potassium hydroxide, how many grams of water, so we're looking for the theoretical yield, will be produced if 100 grams of hydrochloric acid react with excess potassium hydroxide? So the 100 grams of hydrochloric acid, those are acting as our limiting reactant. We're going to use that to determine how many grams of water that we're going to produce. Now the first thing that we have to make sure of is that we have a balanced equation. And in this case we do. Everything looks balanced out. So we're going to take our given, 100 grams of HCl. And pretty much always a standard thing in our problems is to convert from 2 moles. Let's get 2 moles. So we need to know the molar mass of hydrochloric acid. Well, the molar mass of hydrochloric acid is 36.46 grams. And that's the number of grams in 1 mole. We put the grams on the bottom, so they would cancel out with these grams up here. All right, the next step usually is to use what's called the mole ratio. So we're trying to use HCl to predict how much water will be made. So we're using the coefficients in front of HCl and the coefficients in front of water. Well, in this case, there's not a coefficient in front of either one, so the coefficient is implied to be 1. So the mole ratio here is 1 mole of HCl, which we put on the bottom, so it'll cancel out. For every 1 mole of that we use, we should get 1 mole of water. Again, the moles of HCl cancel out. This problem, though, was asking us for what mass of water. So we're looking for grams. So we need to go one additional step. We're going to put 1 mole of water down here on the bottom. And we're going to put the molar mass of water up on the top. Well, the molar mass of water is 18.02 grams. And again, the moles of water had to go on the bottom, so they'll cancel out. So now to get our answer, it's a matter of multiplying across the top, 100 times 1 times 1 times 18.02, dividing by the bottom, so divided by 36.46. The only thing else we had were ones. So when we do the calculations, we end up with a theoretical yield here of 46.9 grams of water. So that's how much water we should get under perfect conditions if we start with 100 grams of hydrochloric acid and extra potassium hydroxide. So now we'll move on to problem 7. If 50 grams of fluorine react with 75 grams of sodium chloride, what is the expected yield of chlorine in grams? First thing that we have to do, since we know amounts of two different reactants, is we have to determine which one of those is limiting. So we need to take either one of them. In this case, I'm going to start with the fluorine. We could just as easily start with the sodium chloride, but I'm going to start with the fluorine. So we're starting with 50 grams. Before we even get started here, make sure your equation is balanced, which in this case it is. So, like always, we're going to convert from grams to moles first. So we need to put in the molar mass of fluorine gas, which is 40 grams. What we're going to do on the next step is use a mole ratio to go from fluorine to sodium chloride, because we're trying to figure out how much sodium chloride do we need to react completely with 50 grams of fluorine. So our mole ratio here is 1 to 2. So we're going to put 1 mole of fluorine down here on the bottom, 2 moles of sodium chloride on top, and then our final step is going to be to convert to grams. So 1 mole of sodium chloride. We need to put the molar mass of sodium chloride up top here, and that's going to be 58.44. So notice that all our units canceled out except for grams of NaCl. Let's do the math. Let's multiply across the top, divide by the bottom, and we end up with 146 grams of sodium chloride. So for 50 grams of fluorine, we need 146 grams of sodium chloride to go with that, for them to be in what we call stoichiometric proportions. If we had 50 grams of fluorine and 146 grams of sodium chloride, they would react completely and none of either chemical would be left over. We don't have that. We need 146 grams of sodium chloride, but the problem states that we only have 75. That tells us that sodium chloride is our limiting reactant. All right, so now we're going to take the limiting reactant, sodium chloride, 75 grams of it, and we're going to use that to determine how much chlorine we should be able to produce. So as always, we're going to convert from grams to moles first. So we'll put the molar mass of sodium chloride down here on the bottom, 58.44 grams. That's equal to 1 mole, which we'll put on the top. Grams of sodium chloride cancel out. Now we're going to use our mole ratio, which is 2 to 1. So we're going to put 2 moles sodium chloride down here on the bottom. For every 2 moles of sodium chloride that we use, we should produce 1 mole of chlorine gas. Finally, we want to convert from moles of chlorine over to grams of chlorine, so we'll use the molar mass. 1 mole of chlorine is equal to 70.91 grams of chlorine gas. Moles cancel. So we do the math, and we end up with 45.5 is our theoretical yield. That's how much chlorine gas we should produce if all of the 50 grams of fluorine or all the 75 grams of sodium chloride react. It's probably not really going to happen in the real world, but that's the perfect situation. Now the next problem 8 wants to know if 35 grams of chlorine are actually obtained. So it's saying we didn't get the 45.5, we only got 35. What's the percent yield? What you've got to remember is that the percent yield is equal to the theoretical or expected yield. That's the number. Sorry, let me back up for a second. So the percent yield is equal to the actual yield, what you actually got when you did the experiment, divided by the theoretical or expected, and all that times 100%. So let's make a little space up top here. So for our percent yield, we're going to take our actual yield, which is how much the problem says we really got when we did the experiment, 35 grams. We're going to divide that by our theoretical yield, which is what we got from our stoichiometry problem, 45.5 grams. Notice the grams cancel. We're going to multiply that by 100%. And what we end up with for our percent yield is 76.9%. Notice there's no units because the grams canceled out. All right, let's move on to problem number 9. Problem 9 is also a reaction stoichiometry problem. If 45 grams of calcium react with excess water, what is the theoretical yield in grams of hydrogen gas? Notice this problem didn't give us an equation. So we first of all need to get a balanced equation. Let's write that up here up top. So we're starting with calcium. We're reacting it with water. So this is going to be a single replacement reaction. Metals react with water to give you metallic hydroxides. So the metallic hydroxide here is going to be calcium hydroxide, which is that, plus hydrogen gas. Well, so we need to balance this equation, and it looks like to balance it we need to put a 2 right there. So there's our balanced chemical equation. So now if we go down to the stoichiometry problem, let's take our given, 45 grams of calcium. It says we're reacting with excess water. Well, that means that water is in excess. That means that calcium is our limiting reactant. So we're going to use the amount of calcium to determine the theoretical yield of H2. So first of all, let's convert from grams of calcium to moles of calcium. So we're going to put the molar mass down here on the bottom. That's equal to 1 mole of calcium. Now we're going to use our mole ratio. So we're trying to convert from calcium to hydrogen. So notice there's no coefficient in front of the calcium. There's also no coefficient in front of the hydrogen, which means our mole ratio is 1 mole of calcium to 1 mole of hydrogen. Well, we're looking for the mass in grams, so now we need to convert from moles of hydrogen to grams of hydrogen using the molar mass. The molar mass of H2 is 2.02 grams per mole. So we cancel out all our units. Only thing that doesn't cancel is grams of hydrogen. We multiply across the top. We divide by the bottom. And when we do that, we end up with a theoretical yield of hydrogen of 4.54 grams of H2. Now problem 10 wants to know if the reaction described in the problem above were carried out at STP, what is the volume of the hydrogen gas that is produced? So instead of looking for mass, we're looking for volume. So let's just start back like we did at top. Let's start with the 45 grams of calcium. Just like we did above, convert that to moles. Our next step was to use the mole ratio, which we'll do again. 1 mole of calcium, 1 mole of hydrogen gas. Where this problem differs is on this next step. Remember that 1 mole of any gas at STP is going to be equal to 22.4 liters of that gas. Now remember, that number only works at standard temperature and pressure. Cancel out all the units, multiply across the top, divide by the bottom, and when we do, we get a theoretical yield of 50.3 liters of hydrogen gas. So that's our answer for number 10. So let's move on to number 11. So again, on number 11, we're not given an equation. We're reacting lead 2 nitrate with potassium chloride. And first of all, we want to know which reactant is limiting. Let's first of all come up with an equation. So here's lead 2 nitrate. Been a little tricky there. We're reacting that with potassium chloride. So this is going to be a double replacement reaction. The lead and the potassium are going to switch places. So we're going to end up with potassium nitrate plus lead 2 chloride. We need to balance this equation by putting a 2 in front of KCl. Also need a 2 beside my nitrate there, and a 2 right there. Alright, and make sure, don't let me confuse you, the subscript that I put beside the nitrate, I should have put that there before I started balancing. The correct formula for the compound lead 2 nitrate is Pb quantity NO32. So now let's start by looking for our limiting reactant. Remember, we could start with either the amount of either reactant and use that to determine the limiting reactant. So I'm going to start with the lead nitrate. So we had 200 grams of PbNO32. As always, let's convert from grams to moles first. The molar mass of lead 2 nitrate is 331.20. That's 1 mole. Alright, so let's do a mole ratio. We're trying to figure out how much potassium chloride we need to be in stoichiometric proportions with 200 grams of lead nitrate. So our mole ratio here between lead nitrate and potassium chloride is 1. Again, the mole ratio is 1 of these to 2 of these. So 1 mole here, and that's 1 mole of lead nitrate, lead 2 nitrate. For every 1 mole of that you use, you need 2 moles of KCl. Finally, we need to convert to grams of KCl. So 1 mole KCl. Put the molar mass of potassium chloride up top, 74.55 grams. Cancel out all our units. And again, note that everything cancels except for grams of KCl. Let's do the math. And we get an answer here of 90.04. And remember, that is grams of KCl. So what this is telling us is for 200 grams of lead 2 nitrate, we need 90.04 grams of potassium chloride to go with it. Well, the problem told us that we had 150 grams of KCl. That means that we have way more than we need. So again, we need 90.04 grams of potassium chloride, but we actually have 150 grams of potassium chloride. That means that we have way more potassium chloride than we need. Therefore, lead 2 nitrate is the limiting reactant. So we're going to use the amount of lead 2 nitrate, the 200 grams. We're going to use that to calculate the theoretical yield of lead 2 chloride. So like always, take our given, convert that over to moles, exactly like we did in the problem up top. So 331.2 grams of lead 2 nitrate is equal to 1 mole of lead 2 nitrate. Let's do a mole ratio. Our mole ratio between lead nitrate and potassium lead chloride is a 1-to-1 ratio. And our final step is to convert from moles of lead nitrate, lead chloride rather, to grams of lead chloride. So we use the molar mass. The molar mass of lead 2 chloride is 278.10. All right, all our units cancel, except for grams of lead 2 chloride. And when we do that calculation, we end up with 167.9 grams. So that's how much lead 2 chloride we should get if all 200 grams of lead 2 nitrate react completely. Problem 13 tells us if 100 grams of lead 2 chloride are actually recovered, what's the percent yield? Remember that the percent yield is equal to the actual yield, which in this case is 100 grams, divided by the theoretical yield, which we calculated in our problem number 12 to be 167.9 grams, times 100%. So we do the math on that, calculate it out, and we end up with 59.56% yield. All right, so now we're on to problem 14. Another reaction stoichiometry problem. If 55 liters of oxygen gas react at STP with 35 liters of hydrogen, what is the theoretical yield of water in moles? So like before, we need a balanced equation first. So we're starting with oxygen gas, which is O2. We're reacting with hydrogen gas, which is H2. We're making water, H2O. We need to balance this equation. We're going to have to put a 2 right here and a 2 right there. So that's our balanced equation. Now we're going to start with our given. We're assuming, well, we've got to determine which one of our reactants is the limiting reactant. So we could start with either one. I'm going to start with the oxygen. Like always, we're usually going to convert our given to moles if it's not already in moles. Since we're at STP, there's 22.4 liters of any gas in 1 mole of that gas. Our next step is almost always to use the mole ratio. We're trying to figure out how much hydrogen we need to go with 55 liters of oxygen. So we look at our mole ratios, no coefficient in front of the oxygen. We've got a 2 in front of the hydrogen. So our mole ratio is 1 mole of O2 for every 2 moles of H2. And that's as far as we need to go. Notice that all our units have canceled out except for moles of hydrogen. So now we can multiply, and when we do, we get 110. But back up, we need to go one more step. Since we were given liters, let's go ahead and convert from moles of hydrogen to liters of hydrogen. So at STP, 1 mole of hydrogen is 22.4 liters of hydrogen. Notice that everything cancels out except for liters of hydrogen, multiply across the top, divide by the bottom, and when we do, we come up with 110 liters of hydrogen. So for 55 liters of oxygen to react completely, we need 110 liters of hydrogen. Well, we don't have 110 liters of hydrogen, we only have 35. That tells you that hydrogen is the limiting reactant. So to determine the theoretical yield of water, we need to use the hydrogen, not the oxygen. So now let's start with our 35 liters of hydrogen, our limiting reactant. Let's convert that to moles using 22.4 liters in 1 mole. Let's do a mole ratio between hydrogen and water. I erased our balanced equation up here, so let's put it back up here. So there we go. So our mole ratio between hydrogen and water is 2 to 2, or we can reduce that down to 1 mole of hydrogen to 1 mole of water. We're looking in this case for moles of water. So this is as far as we need to go. We've now canceled out all our units except moles of water. We now multiply across the top, divide by the bottom, and we end up with a theoretical yield of water of 1.56 moles of water. And that's it for problem 14. One more problem to go, problem 15. So for problem 15, if 45 grams of calcium react with 95 grams of copper 2 nitrate, what's the theoretical yield in grams of copper? So again, we need a balanced equation. Let's write this up top. Starting with calcium, we're reacting it with copper 2 nitrate. This is going to be a single replacement reaction. Calcium is above copper on the activity series, so this reaction will happen. We'll end up with copper metal plus calcium nitrate. Check to see if it's balanced, and that equation is balanced as written. So now we need to determine the limiting reactant. Again, we can start with either of our reactants. I'm going to start with the copper 2 nitrate in this case. So we're going to say 95 grams of copper 2 nitrate do our chart. Use the molar mass. Molar mass for copper 2 nitrate is 187.56. That's the mass of 1 mole. We need to do a mole ratio between calcium and copper 2 nitrate. And all of our coefficients are 1, so that's going to be a 1-to-1 ratio. And then finally, convert from moles of calcium to grams of calcium. And the molar mass of calcium is 40.08. So notice everything has canceled except for grams of calcium. We do the math, and we end up with an answer of 20.3 grams of calcium. Well, that means for the 95 grams of copper 2 nitrate, we need 20.3 grams of calcium for them to be in stoichiometric proportions. But the problem tells us that we actually started with 45 grams of calcium. That means we have more calcium than we need. Calcium is the excess reactant, which means copper 2 nitrate is the limiting reactant. So we need to use the 95 grams of copper 2 nitrate to calculate the theoretical yield of copper. Alright, so let's take our 95 grams of copper 2 nitrate. Let's convert from grams to moles. The molar mass of copper 2 nitrate again is 187.56. Now we're going to do a mole ratio. We're trying to determine how much copper metal we can make from this. So our mole ratio is 1 here, 1 here. And then finally, we need to convert from moles of copper to grams of copper, realizing that the molar mass of copper is 63.55 grams. Cancel out all our units except for grams of copper. Go ahead and do the multiplication and the division on bottom, and we end up with a theoretical yield of 32.2 grams of copper. All right, that's the end of our stoichiometry practice problems, and I hope that helped.